Okay, so this is a UTF-8 length function. This essentially takes in a string, and this is written in C because C doesn't have native UTF-8 functions. You have to use a library. Many other languages already have it built in, so C is also simple enough to kind of show how these, or to do these problems just because out of necessity, I guess, in that case. So I wanted to create a UTF-8 length function that didn't use if statements. A lot of the functions you come across on the internet with Stack Overflow or whatever, they use if statements and branching, and I wanted to do it without branching whatsoever, just pure math. And that's not to say this is going to be faster. It likely will be with optimizations, but branching on, say, if it's just all English, the if statements may even be faster because it's the CPU can assume, even if it assumes wrong, in most cases it's going to assume correctly and take the correct branch. So you always need to test your performance of your code. But this is an example of something you could do to prevent any branching if you just don't want any branches. Now this is the optimized version. We're going to be taking a look at this one. It's a little bit easier to read to start, but they're the same. Just this one is simplified. So to start, we're going to take a look at an ASCII table real quick, refresh our memory. This is an ASCII table of printable characters, so we're going to start here at 32 instead of starting at 0. But we're going to end on the correct number, which is 127. And you can see this is just a list of characters. You go down the decimal side, you're going to see a list of characters that are going to be printed or associated to this this mapping. So we say when we see the number 77 or the hexadecimal number 4D, we're going to put the capital letter M. So that just goes down. We have some symbols and then all of the English characters here, the capital and lowercase. And then we end at 127. So now let's take a look at UTF-8 and the encoding. So UTF-8 is an extension of ASCII. So it basically overlays on top of ASCII. ASCII stays exactly the same, and UTF-8 then uses the extra bytes that come after the ASCII character, if it's not an ASCII character. So what you'll notice here is in this first row here, we have 1 byte. So if it's a 1 byte UTF-8, these are the characters. The X's are the characters that are usable. So you can notice that the last bit is not used. If we put a 1 here and all of these were zeros, this would be 128. So notice that the ASCII table ended at 127, giving us that extension bit there, which is critical to how UTF-8 works. UTF-8 essentially takes use of that control bit and to denote the rest of the sequence. So you'll notice here in all of the bytes that precede it and all the other formatting, the first bit is always set in every single instance. Or not the first bit. Let's just call this the 128 bit or the 8th bit. This one on the far left, to keep it simple, is always set on all of them. And that's partly for error checking. So as we're reading the bytes, we know that if we put a 1 in this one and we go to read the next byte and there's a 0 there, that bit's not turned on, then we have an error, and this is an incorrectly formatted UTF-8 string. We're actually probably reading some other kind of data that's not UTF-8. So this is a nice cyclical, because not cyclical, but it's a nice error checking as you go through the bytes to read the UTF-8 character. So we have this one is ASCII, and then you'll notice there is 2 bits that are turned on in the next one, 3 bits that are in the next one, and 4 bits that are in the next one. And then all the remaining bytes have the same exact beginning control characters of 1, 0. So with this pattern, it starts to show us what happens when we have two bits on here. We can imagine there are 2 bytes. When there are 3 bits on, we can imagine there are 3 bytes. When there are 4 bits on, there are 4 bytes that we read. And then the remaining is the data for that UTF-8 character that we will that encoding. But we're interested in the length of the string. Just using this information of these bits, we can deduce the length of the string. If we have 4 bits on in the beginning, then we know we have 4 bytes. If we have 3 bits, it's going to be, we know that we have 3 bytes. If we have 2 bits, we know that it is 2 bytes. So we can take that information and we can now look at what we have here for our UTF-8 length function. We're going to use just the top one first, and we'll look down on the second one. So the first thing is we take in a string, of course, to this is just a character array that we take in so that we can see the string itself, and we can count each one of its characters. We start off at 0. When we hit the null terminator, we exit the loop. So of course, if we just pass in a null terminator, we're going to return 0 out of here. But let's imagine that we passed in some ASCII values. So let's look at this table here. See if we can get the table and the code here. Okay. So let's just imagine that we passed in this case here where we have 110 and 10 and these 2 bytes. So if we passed in and we read the first character and we saw these 2 ones, we knew we'd have to read 2 bytes. So what happens here? We have 8, 4, 2, 1, or 80, 40, 20, 10, however you want to say that in hexadecimal. And let's just be clear on what our columns are here. Let's mirror this 1, 1, 0, and let's just 0 out everything else. So there's 4 bits, 5, 6, 7, 8. There's our 8 bits that make up our first byte here. So this first one is going to be 0. Or let's just say it's 80. Let's less things to write on here. The second one is going to be 40. Third one is going to be 20. Fourth one is going to be, put the arrow the wrong way. It's going to be 10. And then of course we have the remainder, which we're not actually interested in, but let me just draw in the arrows. 1, 2, 4, and 8. So that's what all these bits are. So we're interested in the top 4 here, which is going to be 80, 40, 20, and 10. And that's what we see here. So we're masking the byte by 80. So of course that 80, so 0, 0, x80 is going to be equal to 1, 0, 0, 0, 0, 0, 0, 0. 40 is going to be the next one. So 40, 20, and 10 are going to be respectively 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, and then 0, 0, 0, 1, 0, 0, 0, 0. So you can see that it makes a diagonal line essentially here. So if we shift by 7 bits to the right in this first example, we're essentially taking this 1 and putting it all the way at the end. If we're shifting by 6 bits, we're taking this 1 and putting it all the way at the end. So essentially what we're doing here is we're putting all of them at the end, the far right end. So that I'll just do one example here. So if we shifted 0x80 by 7, we would wind up with 0, 0, 0, 0, 0, 0, 0, 1, where it's essentially flipped, where this is all the way at the end. It's not flipping though, because remember this one gets pulled over by 6, so 1, 2, 3, 4, 5, 6. It goes to the end. This next one is 5, and so we go 1, 2, 3, 4, 5. So notice they all end up at the end. So that's what we're going to be setting in V0, V1, V2, and V3. So essentially these numbers, V0, V1, V2, and V3, they are all going to be either 1 or 0, because we've masked it and we shifted the bit all the way to the to be bit number 1. So all of these values are 1 or 0. So let's take a look at this first example. It is 1, 1, 0, 0. So 1, 1, and then all the rest zeros, because we're doing 2 bytes. So this is essentially going to be equal to 1, and this is going to be equal to 1. This is going to be equal to 0, and this is going to be equal to 0. We just take those control characters and put them into the V's. Ignore the 1 plus for now, but you see we have v0 times v1. That's going to be v0 times v1. This is going to be 1. Then we have v0 times v1 times v2. Because v2 is 0, this whole thing is going to be 0. Because anything times 0 is 0. Same thing here. This whole thing is going to be 0. So essentially what we're doing is we're doing 1 plus 1 plus 0 plus 0. So what is 1 plus 1? That's 2. We got our two bytes. It's our 2-byte character. So let's imagine that we were dealing with this next one where we have 3 and then a 0. So in this case it's 1 1 1 0. So this would be 1. Remember v2 is now 1, so this would become 1 because it's v0, v1, and v2, 1 times 1 times 1, and then 0. So we have 1, 2, 3. And likewise, if we do the last one, you'll see that this becomes 0, and we have 1 plus 1 plus 1 plus 1, which is 4. So we're essentially just counting those bytes using those control bits very easily. So we take this logic of counting the control bits, and then we're going to reduce it into this function here, which was, I don't know if I said it, but this was by Max Breyer. He simplified it once he read how he did it. He simplified it down. And it's pretty straightforward how it's simplified. Notice that v0 and v1 are always multiplied by each other in every case, in all three of these. So you could just say, okay, so we don't need v0 and v1. All we need is v0 times v1 combined. So we get that here, where we, so essentially, let me simplify this. Let's imagine that we had this case here, where it's an ASCII character, right? So we have this case here where it's 0 all the way across. Right? So this is going to produce 0, and this is going to produce 0. So 0 and 0 are going to be 0. So v01 is going to be 0. Now let's imagine that we have this second case, 1, 1. Let's imagine we had a wrong case, so one that's not valid, which is a 1 and a 0. In that case, this would make this 1 and this one 0, which is also going to be 0, because if you mask them together and it's 0 and 1, you're going to get a 0. So this kind of this would produce this would produce a 0 in the error case as well, which is fine because we actually have a separate function for validating UTF-8 down here. So I don't like to mix validating and processing in the same function if I don't have to. So we run through like everything's normal in both of these cases. So essentially we're just doing the multiplying of those two together to concatenate them into either a 0 or a 1. So v01 is going to be 0, 1, which replaces all of these, you can imagine. 1 plus v01 plus v01 times v2 plus v01 times v2 times v3 would be the first simplification there. We keep our v2 and v3 and with the same masking that we had prior. But now we've simplified it even further down here. We say 1 plus, and then we take v1 and we shift it by v2. So let's take this first case here where we have 1, 1, 0, right? And that first case was this column, 1, 1, 0. So v0 and v1 are 1, v2 and v3 are 0. So if we took v1 and we shifted it by v2, which is currently 0, it's just going to be v1 by itself. Let's imagine we're in that second case where it's 1, 1, 0, 0, right? So these two are combined here. So v01 is equal to 1, and then these are equal to 0, 0. So this is just going to remain 1 because we're not shifting it at all. And then we're ORing v1 and v3. So v1 and v3, since v3 is 0 here, that makes this whole thing 0 because they're ANDing together. So if we OR a 0, it's just going to be itself. So it's going to be 1 plus 1 is 2. So now let's take the next case where it's 1, 1, 1, 0. So let's put a 1 here and a 0 in this case. So here now we have V1 shift by V2, and V2 is 1. If we shift 1 over one place on the left, so if we had 0, 0, 0, 1, right? Let's just deal with 4 bits here, and we shifted it one place here. We now have the value 2. We have 0, 0, 1, 0, which is equal to 2. So essentially we're saying 1 plus 2. So, well, not yet, but this is going to be 2. And this is going to be 0 again. So if we OR 0, it's going to be 0. So it's going to be, this is going to be 2. So it's 1 plus 2 is 3. So you see what's going to happen here. Now if we have them all 1s, we have 1 here, 1 here, and 1 here. We already know what this case is because we've just done it. And now let's look at this. So this is going to be V1 and V3. Both of these are 1, so it's going to be 1. So this mask here is going to be 0, 0, 0, 1, right? And we've shifted 1 to the left by 1. So this mask is going to be 0, 0, 1, 0, right? And if we mask those together with the OR operator, we're going to end up with 0, 0, 1, 1, right? Which is the value 3. Right? We have 1 bit here for 1, 1 bit here for 2, 2 plus 1 is 3. So we have 3, so it's going to be now 1 plus 3. And so we have the same exact code as we do up here with a few less instructions and a little bit more bit operations rather than multiplications. So that's essentially how the UTF-8 string length works. Sorry if we got into some deep details here with all the bits. I know it can be a little bit hard to follow, but that's essentially how we read it. Then we come down here to the validate function, which is it's pretty straightforward. We see down here, I'm using the original multiplication version to go to the next character. Essentially this whole section here is, our go to next character, go to next, which is just the same exact code as counting the characters instead of a UTF-8 string, right? Same exact thing. So you can of course just take this reduced version and put it here and it will work the same way. What we are interested in here is the validation here. You'll notice that we don't have any, we still don't have any branching outside the original null check. If it's null, it's not valid. You could, you could treat null as valid in your case, but I don't. So then we go to the character. We say that it's originally valid, right? We start off valid. Everything's good, and then of course we're returning down here whether it's good or not, depending on this for loop. Of course, if it's a null terminated string where 0 is the first character, it's going to skip this and return the true. Now, same thing. This is essentially the same, like stir here, just inside of a character. We're using a C proxy, probably because originally this was a char star constr. But anyways, details aside, we go to do this validation, and we're doing this validation. And notice what we're doing. Remember what this 8 is. E is new, and yeah, I guess it would be important to know which each one of these come out to be. Okay, so I'm just going to go down the line here where we have our first one, which is going to be 8. So we have 8 is going to be equal to, let's just talk about, notice how it's 0 in all of these, but we do have an 8 there, some zeros there. So the last 4 bits are mostly going to be, mostly all going to be zeros. So 8 or 80 here is going to be 1 and then followed by 7 zeros. 4, 5, 6, 7. E is going to be, let's put an E, it's going to be 1, 1, 1, 0, 0, 0, 0, 0, right? And then F is going to be 1, 1, 1, 1, 0, 0, 0, 0. And then F8, you can imagine it's the same thing here. If an F is 4 bits turned on, then F8 is going to be equal to 1111 for the F, 1 for the 8, and then 3 zeros, right? And then we have our C, which is going to be, I'm running out of space here, C, which is going to be equal to 1100, and then all the rest zeros, 1, 2, 3, 4, right? Let's see, what else do we have? E we already covered, F we already covered, C we covered, 8 we've covered, and C and 8 we've covered. Okay, so we've covered all the cases now for this. Now let's look at the first bit mask, that's an 8, which is going to be this first one here. So we're saying if 8 is 0, then if 8 is 0, we know it's ASCII, or we're saying that it's going to be ASCII in this case, right? Because if we look at the ASCII table, the first bit here, which would be the 8, is 0. So if we have 8 is 0, we're saying, okay, so far it's good, it's ASCII, right? So we're going to say, yes, it's valid so far. This is an ASCII character. Otherwise, if it's not 0 and it is 1, that means that it's going to either be 2 bytes, 3 bytes, or 4 bytes. And that's essentially what we're doing here. We're saying, okay, since 8 is not 0, which means it's automatically 1, we're going to check E case. So we're going to check for 3 ones, right? So if these 3 are equal to C, which is these two, so we're masking, we're taking this mask, and when we're saying if it's this, if we say 111 is 110 in the case of what we're reading. So let's take an example, because this is getting in the weeds a little bit. Let's go back to our example 100 for a 2-byte character. So let's say 110 is our 2-byte character. This means we have 2 bytes coming in. If we mask our against E, our character, which is 111, we should get 1 and then 1 and 0 are going to be 0. So our output should be 110, which is C. So if those are equivalent, then we know we are indeed a 2-byte character. But now that we've discovered we are a 2-byte character, remember we need to check our next byte to ensure that it has the correct control bits of 10. And we do that repeatedly for all the rest. So when we do that validation, we're going to check, okay, we've checked the first character. It is indeed a 2-byte character. So let's check the next byte and ensure that when we do a mask of C, which is 11 and then a bunch of zeros, against it, we get 10 in our beginning. This is this 8, right? Because we're only checking the first 2. So this is if it's ASCII, this is if it's 2 bytes, that means this is if it's 3 bytes, and this one's going to be if it's 4 bytes. Very simple. You just extrapolate from there. It just does the same thing where it checks each one of the next bytes to ensure that they are valid encoded characters. Now this part I think can be simplified. I didn't spend a whole lot of time trying to simplify this portion, but I think it can be simplified because all these bytes here at the end line up, and there's probably something you can do there. But that's how you check the UTF-8 valid. So like I said, I do them separately. I would validate the string that comes in from some unknown location, and then I would get the length for it and operate on it if it is valid, and I would separate those two out so you're not checking if it's valid every time you do a length comparison. You can validate early and assume later on, kind of a scenario. So there you go. Branchless UTF-8 length function, and I mean technically you've got these OR branches internally, so this is not a branchless valid UTF-8, but I think that this can become branchless. My main focus was the UTF-8 length, so maybe I'll come back to the UTF-8 valid and think about it and try to make this one truly branchless without all of the ands and ors. But it's going to be difficult because you got to check bytes, and you only know the extra bytes exist if the previous one are a valid character. So you don't want to read outside the bounds of the array. So it gets a little hairy there, and it may not be possible, but simplification may be, still possible. I'm rambling. I really enjoy working out these puzzles. These ones, like I said, I worked out this one just because I wanted a branchless UTF-8. And if you want to use this, go ahead. And this is a nice update to it that I have now in my library of C code. Cool. If you have any questions, let me know. Sorry if this got a little bit in the weeds. It's very hard not to get in the weeds when you're talking about bits. You wind up saying 10111010 so many times that it can get confusing to people. But if you have any questions, let me know. I can always follow up with this and see if I can simplify it. But yeah, there you go. UTF-8 length and in C, and you can port it to whatever language you want.